Hello everyone, and welcome to our videos. Today we have two lectures. The first lecture is Cayley's formula. We will study another proof of Cayley's formula. The lecture has three parts. First, we will learn what is a directed graph. Then we will show the second proof of Cayley's formula. The last part is examples of the second proof. What is a directed graph? Before learning the definition of a directed graph, we recall the definition of a graph. A graph is a pair of sides. The first side, V, is a set of vertices, and the second side, E, is a multi-set of unordered pairs of vertices. In a directed graph, every edge should have a direction. So the set E in a directed graph should be a multi-set of ordered pairs of vertices. This is the only difference. So the definition of directed graph is a directed graph G, sometimes we call it a digraph for short, is a pair G equals VE, where V is a set of vertices and E is a multi-set of ordered pairs of vertices. In other words, a digraph is a graph where each edge is assigned a direction. Here are two diagrams. The left one is a normal graph, and the right one is a digraph. We can see the only difference between a graph and a digraph is that in a digraph, every edge has a direction. In the left graph, if we give each edge a direction, then it becomes a digraph. We can find a triangle in each of the digraphs, but the two triangles are in fact different. Actually, the left triangle, in fact, is not a directed cycle, but the right triangle is a directed cycle. A directed cycle is a cycle in which each edge is traversed in the same direction. So in the right triangle, we have 2 to 3, 3 to 4, 4 to 2. This is a directed cycle. But in the left triangle, we have 2 to 3, 3 to 4, but 4 cannot go back to 2. So this is not a directed cycle. We see that the edge between the vertices 2 and 3 in the right graph is from 2 to 3. We can add another edge from 3 to 2. The right graph now is still a simple digraph because the edge 2 to 3 and the edge 3 to 2 are different edges because now each edge has a direction. Now we consider another basic definition of directed graph: out degree and in degree. Let V be a vertex in a digraph. The out degree, whose notation is D plus V, is a number of edges with V as its tail. In other words, it's a number of edges leaving the vertex V. The in degree, whose notation is D minus V, is a number of edges with V as its head. In other words, it's a number of edges coming into the vertex. Now, let's take an example. In this digraph, let's calculate the out degree and in degree of the vertices 10 and 4. We see that there is no edge leaving the vertex 10, so the out degree of 10 is 0. And there are 3 edges coming into the vertex 10. So the in-degree of the vertex 10 is 3. There are 2 edges leaving the vertex 4. So the out degree of 4 is 2. And there are 2 edges coming into the vertex 4. So the in degree of 4 is 2. We will use the definition of directed graph to give a second proof of Cayley's formula. Now let's recall Cayley's formula. Cayley's formula tells us that there are n to the power n minus 2 trees with the vertex site 1, 2, 3 up to n. We have learned the first proof of Cayley's formula. It's called puffer code. Iteratively delete the leaf with the smallest label and add the label of its neighbor to the sequence. After n-2 iterations, a single edge remains, and we have produced a puffer sequence, or a puffer code, or puffer numbers of length n-2. We can prove that there is a bijection from the set of all trees on n vertices onto their puffer codes, because there are n to the power n-2 puffer codes. So our proof is done. This is a sketch of the first proof. Now let's go to the second proof. This proof is given by Royal in 1981. First, let Tn be the number of labeled trees on n vertices. We need to prove that Tn is equal to n to the power n-2. For each labeled tree, we will choose 2 vertices from the tree, called L and R. L and R can be the same vertex. For a tree of order n, we can choose any vertex from the n vertices to be the vertex L, and we can choose any vertex of the n vertices to be the vertex R. So both L and R has n choices. Now let Tn be the family of labeled trees with 2 distinguished vertices L and R. Clearly, the size of capital Tn equals lowercase tn times n squared. This is because there are Tn labeled trees, but we need to choose a vertex to be the vertex L. There are n choices, and we need to choose a vertex from the n vertices to be the vertex R. There are another n choices, so the total size is Tn times n times n. So to prove the lowercase tn equals n to the power n-2, it's enough to prove that the size of capital Tn is equal to n to the n's. This is an example of the tree with 2 vertices. There is only one tree with 2 vertices 1 and 2. But we need to find the vertices L and R. Both L and R have 2 choices, so there are 4 trees with 2 special vertices. So how to prove the number of capital Tn is n to the n's? We know that the number of all mappings f from n to n is n to the n's. The f is a mapping from n to n. A1 is an image of 1, A2 is an image of 2, up to An is an image of n. Here each AI has n choices from 1 to n. So the number of mappings equals n times n times n times n. There are n n's, so it equals n to the power n. So to prove Tn equals n to the n's, we'll describe a bijection between the set of all mappings to Tn. So let F be a mapping. We can get a directed graph GF from the mapping F, whose vertex site is n and whose directed edge site has n elements, from 1 to F1, 2 to F2, up to n to Fn. Let's take an example. This is a mapping F. We can get a directed graph GF from the mapping F. The image of 1 is 7, so we have a directed edge from 1 to 7. The image of 2 is 5, so we have an edge from 2 to 5. The image of 3 is 5, so we draw an edge from 3 to 5. The image of 4 is 9, so we draw an edge from 4 to 9. Following the same procedure, we draw edges from 5 to 1, from 6 to 2, from 7 to 5, from 8 to 8, from 9 to 4, from 10 to 7. Now we have obtained a directed graph GF from the mapping because each number appears exactly once in the first row of the mapping. So we can see that GF is a digraph in which the outer degree of every vertex is exactly 1. There are 3 components in this graph GF. In each component of GF, the number of vertices equals the number of edges. This is because for each vertex, there is exactly 1 edge leaving the vertex, though the numbers between vertices and edges are the same. So we find that each component contains exactly 1 directed cycle. Remember that our purpose is to find a bijection between the mappings and the labeled trees with 2 special vertices. Here we have found a directed graph. Now we need to get a special tree from the directed graph GF. So let M be the union of the vertex size of these cycles. In order to create a tree, we need to get rid of these cycles. We need to destroy these cycles. It's easy to see that F restricted to M is a bijection. We see that M has 6 vertices, 1, 7, 5, 4, 9, 8. F restricted to M is from 1 to 7, from 7 to 5, from 5 to 1, 4 to 9, 9 to 4, 8 to 8. This is a restriction to M. We see that this is a bijection from 1, 4, 5, 7, 8, 9 to 1, 4, 5, 7, 8, 9. Because M is the union of these cycles. So F restricted to M is a bijection. And M is the unique maximal size with this property. We see that M has vertices 1, 4, 5, 7, 8, 9. Now let's write down M and F restricted to M. M is 1, 4, 5, 7, 8, 9, and F restricted to M is, the first row is 1, 4, 5, 7, 8, 9, and the second row is 7, 9, 1, 5, 8, 4. And we should write f restricted to m such that the numbers in the first row appear in natural order, is in increasing order. And this gives us an ordering of m according to the second row. For f restricted to m, the first row is v1, v2 to vk. The second row is fv1, fv2 to fvk, such that v1 is less than v2, less than up to less than vk. We can choose fv1 as a vertex L and fvk as a vertex R. So here, in this example, we choose 7 as a vertex L and 4 as a vertex R. Now, the tree T corresponding to F is constructed as follows. Draw a path fv1, fv2 to fvk and fill in the remaining vertices as in GF. Now we draw it in this way. First, we draw a path 7, 9, 1, 5, 8, 4. 7 is the vertex L and 4 is the vertex R. Now there are 4 remaining vertices, which are 2, 3, 6, and 10. We see that the image of 2 is 5, so we have an edge between 2 and 5. The image of 3 is 5, so we draw an edge between 3 and 5. 6 is mapping to 2, so we have an edge between 6 and 2. The last edge, 10, is mapping to 7, so we have an edge between 10 and 7. This is the tree T corresponding to F. Let's recall what we have just done. From the mapping F, we have a digraph GF. And from the digraph GF, we have the union of these cycles M, and F restricted to M. Then we have this tree T. Now let's reverse the procedure. That is, get a mapping from this tree. It is immediate how to reverse this correspondence. Given a tree T with 2 distinguished vertices, L and R, we look at the unique path P from the left end to the right end, that is from L to R. This gives us a set M and the mapping F restricted to M. The remaining correspondence from I to Fi are then filled in according to the unique path from I to the path P. Now let's take an example. How to get a tree with 2 distinguished vertices from a mapping. This is a mapping F. First, we can draw the digraph GF. The image of 1 is 1, so we have an edge from 1 to 1. The image of 2 is 5, so we have an edge from 2 to 5. The image of 3 is 6, so we have an edge from 3 to 6. The image of 4 is 3, so we have an edge from 4 to 3. The image of 5 is 4, so we have an edge from 5 to 4. The image of 6 is 4, so we have an edge from 6 to 4. This is a digraph GF. Now we can write down M M is the union of these cycles. So M has 4 vertices. 1, 3, 4, 6. And then we can write down F restrict to M. The first row is 1, 3, 4, 6. The second row is the images of the first row. Now we can draw the tree T. First, we draw a path 1, 6, 3, 4. We see that here is 1, 6, 3, 4. So we have a path 1, 6, 3, 4. And 1 is the vertex L. 4 is the vertex R. There are 2 remaining vertices, 2 and 5. So 2 is joined to 5, and 5 is joined to 4. Now we have the tree with 2 special vertices. The second example is about how to get a mapping from a tree with 2 distinguished vertices. We can have F restricted to M. The second row of F restricted to M is 1, 6, 3, 4, from the left end L to the right end R. And the first row is the nature order. It's 1, 3, 4, 6. Now we need to map the remaining 2 vertices, 2 and 5. 2 is mapping to 5, and 5 is mapping to 4. This is because 2 is adjacent to 5, so we have 2 mapped to 5. And 5 is adjacent to 4, so the image of 5 is 4. The direction is from the vertex towards to the path. That is from I to Fi. This is lecture 5.1. Thanks for watching.